Hello everyone, welcome to this class on finite element analysis, and in this class let's solve another problem on composite wall heat transfer, that is to determine the nodal temperature distribution. And the question is like this: a composite slab consists of three materials with thermal conductivities 20 watts per meter degree Celsius, 30 watts per meter degree Celsius, 50 watts per meter degree Celsius, and thickness of the slab is zero point 0.3 meters, 0.15 meters and 0.15 meters respectively. The outer surface is at 20 degrees Celsius and the inner surface is exposed to convective heat transfer coefficient of 25 watts per meter square degree Celsius and a medium at 800 degrees Celsius, full stop. Determine the temperature distribution within the wall. Okay, now let's try to write the given data as per the question. Now you can just see thermal conductivities of three materials, element 1, element 2, element 3, or material 1, 2, 3 is K1, K2, K3. And then thickness, in the sense it is nothing but the length, elemental length of three elements. So when three thicknesses are given, it's nothing but the elemental lengths of those three elements, L1, L2, L3. Apart from that, they are telling the outer surface is at 20 degrees Celsius. So you know, like, there are, if there are three materials, there will be four nodes, or obviously, I mean, the number of nodes are always one greater than the number of elements. So three materials or three elements means there are totally four nodes. Four nodes means there will be four temperatures. So outer surface means is that, I mean, it's going to be T4. Okay, the inner surface means it's going to be T1. So understand always that. Okay, and the inner surface is exposed to convective heat transfer coefficient. So this H is equal to 25 and it is exposed at the inner surface. So remember that also. And a medium at 800 degrees Celsius. So T infinity is 800 degrees Celsius, full stop. Determine the temperature distribution within the wall. Now understand, like, you see here they have not given any figure because this question itself is sufficient for us to draw the figure. So you will have to draw the figure by yourself. So it's quite easier. You can just draw a composite wall first. So just a wall over here, and the composite wall, I mean, the thickness is 0.3, 0.15, 0.15. So second and third, let's try to represent it in at equidistant like that. So let this, the first element, be little bigger. So length L1 is 0.3 meters, while length L2 is 0.15 meters and length L3 is 0.15 meters. So apart from that, what else we can write is the temperature distribution. So here the temperature distribution, so T4 is found to be how much? 20 degrees Celsius. So it's nothing but the outermost surface, it's found to be 20 degrees Celsius. And then we have, and they're also telling the inner surface is exposed to convective heat transfer coefficient. So how do you represent that? Is that the inner surface, in the sense it's on the left hand side. Okay, so here you can just mention it as ht infinity. So ht infinity means, or you can just indicate it with h. So h means also it is I mean, it indicates that convective heat transfer coefficient. So this is all about the diagram. You can also mention 1 2 3 4, that it also indicates t1, t2, t3 and t4 at node 4. So now, okay, we have just drawn the diagram. So before proceeding to the problem, first what thing we have to check is the SI units. Just check all the SI units are in, I mean, all the parameters are into the same SI units. You can just see watts, meter, Celsius, watts, meter, Celsius, watts, meter, Celsius. It is in meters anyways, no problem. It is in Celsius anyways, no problem. Meter square, watts. So all those parameters are either in degrees Celsius or watts or meters. So there are no any centimeters or Kelvin, anything. So no need of any conversions, directly we can start with the problem. So first things, the solution. So let me just go to the solution. The first step will always be the easy one, that is the FEA model. So I've just taught you in the last video as well, that is based on this composite wall. So let me try to draw that. So let me try to draw this. So this is node 1, node 2, node 3 and node 4. So here the element length L1 is going to be 0.3 meters, while length L2 is going to be 0.15 meters and length L3 is going to be 0.15 meters. Apart from that, what do we have is we have element 1, element 2 and element 3. We also have T1, T2, T3 and T4. So we also have that as well. So we have element, all that we have just written. So this is all about the FEA model. The second step is elemental stiffness matrix, or you can just in simple words you can just put conductivity matrix. So conductivity matrix. So conductivity matrix, or you can also put as elemental stiffness matrix, still it is not going to change. So the formula is nothing but Ke equal to K into A into L 1 minus 1 minus 1 and 1. So here we have total of three materials, therefore they are going to get it three elements. So K1 equal to capital K1 A1 divided by L1. So small k1 equal to capital K1 is 20. 20 into area, and area is not mentioned here in this problem, but as I told you in the previous class, it's in the previous video itself, whenever area is not mentioned you can assume it to be a1 equal to a2 which is equal to a which is equal to 1 meter square. So assume always it is going to be 1 meter square. So if it is not given, you are going to take it as 1 meter square. 1 divided by length L1 is 0.3. So upon solving this, we are going to get this. So yes, we are going to get that as how much? So we are just going to get that as 66.67. Else we will just try to do it off once. So it is found to be 66.67. 66.67 when multiplied inside, you are going to get it like this. So 66.67. So this is K1. Similarly, when you try to do K2, so K2 when you try to do, you will be getting capital K2, that is 30. 30 into 1 divided by 0.15. So 30 into 1 divided by 0.15. So when you try to do that, you're going to get this answer as 200. 200 when you're multiplying it inside, you're going to get 200 minus 200 minus 200 and 200. And similarly, let's try to do K3. So K3, let me try to show you here. So K3, I mean capital K3 is 50. 50 into 1 divided by 0.15. So 1 minus 1 minus 1 and 1. So therefore the answer of K3 is, so when you try to simplify that, you're going to get 333.33. So minus 333.33 minus 333.33 and 333.33. So this is what you're going to use for the global stiffness matrix. So we all know this is at nodes 1 and nodes 2. This is at node 2 and node 3. And this is at node 3 and node 4. So we have just got it all the three elemental stiffness matrix, or you can also say it as conductivity matrix. So we have just got that. So the next step is, I have just done it already. So you can just check out here. So the stiffness matrix due to convection. So as I told you in this, it is the convection. I mean, they have given in the question itself, the inner surface is exposed to convective heat transfer coefficient. That means the convection is happening on the left hand side. So assume that, not assume, so realize that the convection is happening on the left hand side. I've told you in the last problem itself, whenever if it is happening on the left hand side, the formula is going to be like this. 1 is going to appear here. Suppose if it is happening on the right hand side, 1 is going to come here. It's going to be 0 0 0 1. But as it is acting on the left hand side, it's going to be 1 0 0 0. And even the force vector, it's going to be 1 0 for left hand side. For right hand side, it's going to be 0 1. So don't forget that. So when you try to give area is 1 as it is assumed, and h is 25. So when you are trying to multiply it, you're going to get 25 is multiplied inside. So this is at nodes 1, 2. This is also at node 1, 2. Force vector due to convection, as I told you, if it is subjected to heat transfer coefficient at the left hand side, it's going to be like this. The formula is going to be AH T infinity 1 0. So A is 1, H is 25, T infinity is 800, 1 0. When you're trying to multiply it, you're going to get it 20,000. So it is going to be like this. Next, finally, you have global stiffness matrix. So global stiffness matrix is nothing but K1 plus K2 plus K3, whatever we obtained it in the last page, which whatever I've written. So this is at nodes 1, 2, 3 and 4. I believe all of you know to write the global stiffness matrix. If you still have doubts, you can refer to my previous videos. Now global, so this way I have just written it. So this is now, next is global convection matrix. So we have already got the convection matrix as 25 0 0 0, but as I told, it is only for 2 nodes. Suppose if you have to get it for third and fourth node, so this is only for 2 nodes. But what about the other nodes? Other nodes, you can simply enter it as 0 0. You can just simply enter it as like this 0, because we have just got it for this on the left hand side only 1 and 2, so it's going to be like this. Next, the global force vector. So we have got this for nodes 1 and node 2. At node 3 and node 4, it is going to be 0. Let me directly enter it as 0. So that's going to be like that. So we have just got the global stiffness matrix K. We have just got the global convection matrix H, and we have got this F as well. So now next thing what we have to do is, we have this equilibrium equation. Equilibrium equation, as you know, it is K into T plus H into T equal to F. So here if you take t common, you are going to get k plus h equal to into t equal to f. So k plus h means, you see now in this you have done like, you see this both you have to add. So this is k and this is h. So 66.67 plus 25 is going to be 91.67. Apart from that, all other elements when you are trying to add this, minus 66.67 plus 0 is going to be same. So this k plus h, that's what this both matrices, both are of order 4 cross 4. So you can add both these and just going to write that answer. Only this first element is going to be 91.67. So 91.667. Apart from that, all other elements are going to be the same. So into t means t1, t2, t3, t4, that is equal to 20,000, and apart from that it's going to be 0, 0 and 0. That is the force F value. So now just like last problem however we solved, before applying the okay, we have to apply the boundary conditions. T4 is given 20 degrees Celsius, but before eliminating a particular row or column, what we have to do is we have to multiply any one of this row with this column. So that one is very, very important. But which row will you multiply? That is very important. You know clearly T4 is given. Suppose if I'm trying to if I'm trying to multiply this first row, 91.667 with T1, 66.667 with T2, 0 into T3, 0 into T4. So I will not be able to apply this value of 20 degrees Celsius. It's going to be 0 into T4, 0. So I can't apply this T4 value there. Suppose if it's a non-zero value, apart from 0, if I have any other value like this, if I'm trying to take minus 333.33 into T4 or 333.33 into T4, then I can apply this value of T4. I can multiply with a number and I will get a number. Instead, if I'm taking it, I'll not get. So now first thing we have to choose is, first we have to see the number of rows with least number of zeros. The rows with least number of zeros. First row you have 2 zeros, last row also we have 2 zeros. Okay, let's try to eliminate that. But more importantly, you have to see this one. This T4 means it is fourth node. So this fourth column, the numbers here in this fourth column, wherever you have zeros, you can leave out that rows. You don't have to consider those rows. So here you have 0 zeros. Let me not consider any of this. These two, any one I have to consider. In these two, which one shall I consider? You consider a row which has least number of zeros. Here you have 2 zeros, here you have 1 zero. So you can consider this third row. That is very, very important. So let's try to multiply this third row with this column. So I'm going to get 0 into T1, 0 into T1 minus 200 into T2 plus 533.33 into T3 minus 333.33 into T4 equal to 0, equal to the corresponding element over here, that is 0. So 0 into T1 minus 200 into T2, 533.33 into T3 minus 333.33 into T4. So that one I have done. Now what you have to do is 0 into T1 minus 200 into T2 plus 533.33 into T3. I'm going to send this to the other side. I'm going to get 333.33 into T4. Into T4 is given as 20. So suppose if I am trying to multiply that, so what I'm going to get? So when I'm multiplying this both, I'm going to get 6666.6. So apart from that, this is going to be minus 200 T2 plus 533.33 into T3. So this is what I'm going to get. So now what you have to do is, so now we have got this an equation. Now this value, the 6666.6 that you have to add to here, but where will you add? You have considered this third row, therefore you have to add this to the third element here. So here you have to add that is very, very important. Okay, so now what I'm going to do, I'm just going to rewrite this this matrix. I'm going to modify that and write it like this: 91.667 minus 66.667, then I have 0 0 minus 66.67, 266.667 minus 200, 0 0 minus 200, 533.33 minus 333.33, 0 0 minus 333.33 and 333.33. And here I'm going to write it like T1, T2, T3 and T4. And here I'm going to write it as 20,000, 0, and even also here it's going to be 0. But what is the third element going to be? It's going to be 0 plus 6,666.6. So 0 plus 6,666.6. That is going to be 6,666 only. So now after you can apply the boundary conditions. So applying boundary conditions, I'm going to write BCs. So BCs means boundary conditions. Eliminate, so that is very important. Eliminate fourth row and fourth column. fourth row and fourth column. Why are we going to eliminate fourth row and fourth column? Because the value of T4 is given. So value of T4 is given. Therefore, we are going to eliminate directly this fourth row completely and also this fourth column. So I'm going to eliminate that fourth row and fourth column. So whatever the remaining elements, I'm going to multiply it. I'm going to get 91.667 T1 minus 66.667 T2 plus 0 into T3, that is equal to 20,000. That is equal to 20,000. The second equation is going to be minus 66.67 T1 plus 266.667 T2 minus 200 T3, that is equal to 0. I'm going to get it like this. The next one is 0 T1 minus 200 T2 plus 533.33 into T3, that is equal to 6666.6. So I'm going to get it like this. So now again what you have to do is take your calculator. I mean, in equation mode you can just press the number of unknowns as 3, and there this is going to be A1. So this is going to be A1, B1, C1, D1, A2, B2, C2, D2, A3, B3, C3 and D3. Suppose when you are trying to solve it, you are going to get the values as of T1, T2, T3. So upon solving all those, so I'll just write it like this. On solving, we get the values of T1 as, so if you just take your calculators, you will get it. So I'm going to get 305.25 degrees Celsius. T2 is 119.72 degrees Celsius and T3 as 58.075 degrees Celsius. So you can use your calcs to find out. So T1 you have got it as 305.25 degrees Celsius, T2 as 119.72 degrees Celsius, T3 as 58.075 degrees Celsius. So T4 is already given as 20 degrees Celsius. So you can also see that the temperature is reducing from node 1 to node 4. That means you can assume that heat is flowing from a region of higher temperature to a lower temperature, to a region of lower temperature. Thus your problem is also correct. I hope you have understood this. Thank you.